Hello and welcome to this Isaac Physics tutorial on problem solving using vectors. I'm Michael Conterio and I'm going to be your tutor for today. What's going to happen is I'm going to go through some of the problems that were on the sheet that you got at the vectors workshop that you attended. If you haven't attended one of our vectors workshops, I'm afraid that this tutorial isn't for you, but do keep checking on our Twitter feed and on isaacphysics.org/events. And hopefully there'll be one of those events around near you sometime soon. I'm going to be sharing my screen with you so you can see my workings. And of course, as usual, if you're watching on Isaac Physics website, just make sure you're logged in. And then underneath the video on the event page, you should be able to see a text box, which will enable you to send me messages. And so if there's anything that you're having problems with, anything that I've said that doesn't make sense to you, then send a message in through that and I will check it. One second. There is a slight delay in me getting those, but don't worry, I will read them. And yeah, so if I seem to have gone past something, despite the fact that you said something, then don't worry about it. I'll come back to it later. Okay, so without further ado, I am going to share my screen with you. There we go. I'm going to be working on here. And as I say, we're going to be looking through the Using Vectors in Physics worksheet. So I'm going to start with exercise 8, which says, cosmic rays are charged particles that move randomly in a galaxy as a result of being scattered by randomly oriented interstellar magnetic fields. This process resembles diffusion. In such situations, we can apply a random warp to the cosmic rays, reaching the Earth from beyond our galaxy. Given the dimension of our galaxy is 5 times 10 to the 20 meters, and if the mean free path for a cosmic ray is 3 times 10 to the 18 meters, estimate how long it takes for a cosmic ray to travel across the galaxy. Assume that it travels at almost the speed of light. So what I'm going to do is I'm going to start with a diagram, which is basically something that you should always do. And so we'll have our cosmic ray coming in and bouncing around the place. And then eventually it will end up a distance, capital R, away from where it starts, having and traveled a distance L overall. And the mean free path is kind of like the average of one of these steps. I'm going to call that A. So there's a start. We know from our work early on diffusion that this distance traveled away from the start point, R, is equal to the square root of the number of steps multiplied by the average step length, which is the mean free path in that case. So n equals number of steps. And from this, it should be obvious that the total distance traveled L is just the number of steps multiplied by the average length of the step A. And the time taken for this, T, is the distance traveled, which is L, divided by the speed of the cosmic rays, which is basically the speed of light, C. Substituting in for L, get NA over C. But we don't know what N is. However, if I call this equation 1, and then I say equation 1 squared, I get R squared equals N A squared. And I can rearrange that to get N equals R squared over A squared. So if I label this equation here 2, I can substitute N back into equation 2. So we have T equals NA A over C. So that's R squared over A squared times A over C. That gives you, finally cancelling things out, R squared over A C. And R, A, and C are all things that we know. Therefore, you can use this to solve that problem. Right, so moving on. Exercise 9. The vector capital R is formed by adding the x components and the y components of the lowercase ri vectors whose orientation are random. So what's that saying is that I am going to have lots of little ri vectors whose orientations are going to be all over the place. And then overall, I am then going to end up with a 5 vector capital R. So these are all like R1, R2, and so on and so forth. So, part A. If one of the lowercase ri vectors is projected onto a particular axis, explain why on average the projected value is 0. So I'm going to pick my axis. I'm actually just going to draw a straight up axis here, which I'm going to call my y-axis. There we go. I'm going to put on that. So for any ri that I can pick, the projection onto the axis is that. I can easily pick an opposite vector. So they say this projection is A, this projection is minus A. And so obviously for all of these, there's always going to be an opposite projection. And so the average projected value is going to be 0. Now, the next question, you have to be careful because it says, what is the average value of the vector R? So we actually care about its direction as well as its magnitude. We definitely care about its direction. And so we can write this R as all of these are n vectors. One way to think about it is you can think about projecting this onto an axis. So if I project this onto the y-axis using a vector in a y direction with magnitude 1, this means that for all of those ri's, we get those dotted with y. And since we said that this average is 0, this has got to come to 0. This has got to come to 0. That's not a vector there because it's a dot product. Sorry. And this is true for all coordinate axes. So then you could say R equals 0, 0, 0, which is just a 0 vector. Now, if I just move that out of the way. Part C says, show that R squared, where R is, in this case, is a modulus, not a vector, can also be obtained by adding up the vectors R sub I and taking the scale, that's lowercase r, and taking the scalar product of the vector sum of itself. So we've got saying our r squared, which is given by the dot product of the vector r of itself, is equal to r1 plus r2. These are all lowercase now, r3, so on and so forth, dotted with r1, r2 plus r3, and so on. And that gives us lots of different terms. We've got terms where the two component vectors are the same. So that's r1.r1, r2.r2, and so on and so forth. Oh. But we also get lots where they're different. So r1.r2 plus r1.r3 plus r1.r4. And so basically with these bits, what you're doing is you're basically projecting all the other vectors, all the other random vectors onto an axis. And from before, we've seen that gives you an average 0 projected value. So all this goes to 0, and you're just left with the terms where you have a vector, the dot product between a vector and itself. And there are capital N of these. So we get capital N times the length of one of those vectors squared. So we have capital R squared equals capital N times lowercase r squared. And that gives us r equals square root of n times lowercase r, as expected. Okay. Moving on again, I'm going to now move on to the additional questions. It's unlikely that you got onto these during the workshop, but hopefully some of you have had a go on them. So these are all the projectile questions, all those where basically we end up splitting two different perpendicular directions. So I'm going to draw my definitions of those on here straight away. So I'm going to take y as downwards, and you'll see why in a minute, and x as horizontally to the right. And the reason we're doing this is because we can now completely separate the motion in these two directions. Anything which is happening vertically has no effect on the horizontal motion in these parts of the question, and vice versa. And this is because the only acceleration we've got is vertically downwards. Obviously, you can get some situations where this isn't true. If you have like a charged particle in a magnetic field, it does depend on how the motion is in different directions. But for this sort of projectile motion, the motions horizontally and vertically are independent of each other. And I've chosen y to be positive downwards because g is in that direction as well, and therefore it's just convenience to have the acceleration in the positive y direction rather than in the negative y direction. We'll start with exercise 10. A projectile is fired horizontally off a table at 4 meters per second. It falls towards the ground with an acceleration of 10 meters per second squared. Part A. Calculate the magnitude and direction of the velocity at times t equals 1 second, 2 seconds, 3 seconds, and 4 seconds. So since we've only got gravity acting vertically downwards, then v horizontal constant and is the same magnitude at the start. Vertically, the component is equal to u plus a t, but u in this direction is 0. G, I have to find it to be positive in this direction because I'm taking down as a positive y direction. So it just becomes v vertical equals gt. And so we can draw these. So time equals 0 seconds, time t0, t1 equals 1 second, t2 equals 2 seconds. And so we start off with just our horizontal velocity, v0. After 1 second, we still have that same horizontal component, but we also have a vertical component given by gt1, and so we get this vector as our velocity at that time. And then at 2 seconds, again, we've got the same horizontal component, but the vertical component is now twice the size. V2. And we can always put in angles here and here to the horizontal that the velocity is at. And these are also right angles triangles. And so you can see here the magnitude of velocity and is equal to v0 squared plus gtn all squared and then square rooted. That's just using Pythagoras' law for a right angled triangle. Part B says, how is the velocity related to the flight path of the projectile through the air? The velocity is the rate of change of the displacement of the projectile. The projectile moves along a parabola, and at any point the velocity of the projectile is at a tangent to this parabola. Well, we can work out the horizontal and vertical component of projectile at a time t. So s in the displacement in the y direction is given by u t plus half at squared. And in the y direction, u is 0, a is g. So this is equal to half g t squared. And horizontally, sx, again, we have the same equation of motion, except for the fact that this time our u is our v0, and we have no acceleration. Oops, that should be a plus there. So easy to write the wrong thing. And then yes, you can use this to work out the displacement at the different times. So finally, we are going to move on to exercise 11, which is going to be the last one that I'm going to cover. It says 2 projectiles are fired horizontally in opposite directions at 3.0 meters per second and 4.0 meters per second. At what time are their paths at 90 degrees to each other, and how far have they fallen? This can be done by sketching the diagram of the vectors and algebraically using the vector notation and vector dot product discussed in the concept sheets. So once you've got the time, how far they've fallen is actually relatively simple. That's just the same that as the vertical distance was worked out in the previous exercise, exercise 10. But I am going to do the first part of this question, finding the time. So initially, we have our 2 particles going towards each other with horizontal vectors, horizontal velocities. And then sometime later, these, so that's t equals 0. And then time t later, we still have the same components horizontally because we don't have any acceleration in that direction. But what we do also have is, for both of them, the same vertical component, gt. And now we can draw on our vectors. And also worth noting there, we have got 2 right angle triangles. And we can also join these together at the time when VA and VB are at 90 degrees to each other. And so we've got VA and VB side lengths here. And this side has a length UA plus UB. And so you can see, for example, VA squared is equal to UA squared plus GT all squared from Pythagoras' rule. And then further down here, you can see that the hypotenuse has a length of UA plus UB. Notice this is just the magnitudes of those speeds, not vectors. So that's UA plus UB all squared equals VA squared plus VB squared. And then you can use write a similar equation to this one for VB using this triangle. And then you can substitute both VA and VB into here and solve for the time t. The other way we can do this is algebraically using vector notation. So we can say that VA is equal to UA in the positive x direction. I should actually define my positive directions. Again, I'll do down as positive for y. So VA is UA in the x direction and GT in the y direction. And over here, velocity VB is minus UB in the x direction because it's moving in the opposite direction to the positive x direction. But again, GT in the y direction. And when these are perpendicular, and since for a dot product between, actually I'll just do it for this, VA dot VB is going to give you the modulus of VA times the modulus of VB times cos theta, where theta is the angle between these two velocities. Well, we want this to be 90 degrees, so this goes to 0, and our dot product has to be equal to 0. And that means the other way of writing VA.VB is by multiplying together the x and y, the x components, and adding them to the y components multiplied together. So we get UA times minus UB plus GT divided by GT is equal to 0. And then you just have to rearrange there. Okay, so there you go. There's a quick whistle-stop tour of some of the later questions in the vectors sheets. If you found this useful, good. Do come along to other online workshops that we've got, come along to other in-person workshops, and do go to isaacphysics.org and try some of the problem-solving questions that we've got all across the site. You can find these most easily by clicking the nice question bookmark in the top right-hand corner of the screen. And then you can go there, use the question filter to pick topics you'd like to challenge yourself on. Questions in levels 2 and 3 are about first year of A-level, 4 and 5 are about second year of A-level, and 6 is kind of beyond that if you really want to challenge yourself. They've all got hints in there, particularly a lot of them have video hints. If you really get stuck, you can watch a video which will take you partway through the problem. And also, if you put in a common wrong answer, hopefully then we'll have put in some feedback. Always make sure, if you get the question wrong, that you check to see if there's any feedback given to you as well, because I know some people don't spot that. But thank you very much. I hope you've enjoyed this online tutorial and you enjoy the rest of your day. Thank you very much. Bye-bye.